I will be demonstrating the graphic user interface for the software, Paramagpy. To begin, we will check that we have Paramagpy installed with pip. If you have previously installed Paramagpy, you can include the upgrade flag. Everything looks good, so I'm going to boot the Python interpreter. From here, we can import the GUI module from Paramagpy. Then we can run the GUI. To begin, we can start by loading a PDB file of atomic coordinates. Today I'll be looking at a PDB file of Kelbintin D9K, which is a lanthanide binding protein. We can see here that all atomic coordinates have been loaded into this table. Now I'm going to load some pseudo-context shift data from file. The pseudo-context shifts in this file arise from the binding of the lanthanide, erbium. If we look in the file, we can see that the NPC format contains a sequence identifier, an atom name identifier, the experimental pseudo-context shift, as well as an error which can be set to 0 if unknown. In the main table here, we can see that the experimental pseudo-context shifts have been loaded for the relevant atoms. To display only those rows which contain experimental values, we can click the Hide Not a Number checkbox. Paramagpy displays two tensors here, the initial tensor and the fitted tensor. The initial tensor is used as a starting point for the fitting. Each tensor displays the x, y, and z Cartesian coordinates, the alpha, beta, and gamma Euler angles by ZYZ convention, as well as the axial and rhombic components for the delta chi tensor. In addition, we have this reference parameter, which describes an offset added to all pseudo-context shifts. This may arise due to a referencing error between your diamagnetic and paramagnetic peak lists. Here we can choose a template lanthanide, which is taken from literature. This dataset pertains to erbium, so I'm going to select erbium. You can see that some reasonable values have been set for the axial and rhombic components. The closer this initial tensor is to the real delta chi tensor, the better the quality of the fit, and the easier the job is for the fitting algorithm. In this PDB file, there is a calcium atom which has been included from the X-ray structure. I know that the lanthanide substitutes at this site. By double-clicking this atom, I can set the initial tensor position to the same coordinates as this atom. You can double-click on any row within the table, and you may want to select an atom which you know is close to the binding site of the lanthanide. In this frame up here, you'll see a number of options for the fitting of the delta chi tensor. You can choose whether to fit or constrain the position. Notice that when we choose not to fit the position, that the X, Y, and Z components are set to red. This means that they are constrained during fitting. The fitting of the delta chi tensor is split into two stages: a grid search via the SVD algorithm and a nonlinear regression by a gradient descent. The SVD grid search will solve the delta chi tensor on a grid of points contained within a sphere about the initial starting tensor. For this case, a radius of 5 angstrom will definitely include the metal position. I'm going to set the grid spacing to 0.5 angstrom. We are now ready to fit the tensor by clicking the Fit Tensor button. Notice that the fields of the fitted tensor have been filled in, and that the fitted position is very close to the initial position. Additionally, the Euler angles and axial and rhombic components have also been fitted. The back-calculated pseudo-contact shift values have been filled into the calculated column. We can compare the calculated and experimental values by clicking Plot. Here we observe a high-quality fit, as the experimental and calculated values agree. In addition, you can include some information about the tensor, as well as the atom and sequence identifier for each point. If you were to observe an outlier in your dataset, this allows you to quickly identify it and remove it from the fitting process. In order to disregard a particular experimental data point, you can highlight the row and press X on your keyboard. Notice that the value toggles in this column. If an X is present here, this means that the value will be included during the fitting process. The Q factor, which measures the quality of the fit, is reported here and is very low of about 4%, indicating a high quality fit. To observe the tensor isosurface, we can click the Plot button here. In this case, I want to plot at a contour level of 2 ppm. The isosurface automatically opens in the software PyMol. I would now like to investigate the predicted residual dipolar coupling values arising from this tensor. To do this, I start by clicking the Copy button. Then I navigate to the RDC tab. Here, I am only interested in the RDCs arising between amide HN atoms, so I can check this text box. And here we can paste the tensor that was fitted previously. Be sure to set the right B0 field strength and temperature. We can now calculate the expected RDCs for these amide pairs. Notice that the calculated column has been filled in with the predicted RDC values. We can save these values to a file. In our browser, we can see that the experimental RDCs have been saved to file. I would also like to predict the expected paramagnetic relaxation enhancements. For this, I can navigate to the PRE tab and paste my tensor. Be sure to fit the appropriate rotational correlation time for the protein complex. And we can back calculate the PRE. Notice that the calculated PREs have been filled in the calculated column here. We can plot the isosurface for the PREs with the Plot button. In this case, I am interested in a contour level of 100 per second. This plot says that all atoms contained within this sphere will have a relaxation rate of higher than 100, and therefore we would probably not expect to see them within an NMR spectrum at high field. You are now well on your way to calculating and predicting many experimental paramagnetic NMR phenomena within your protein spectra.